Hello Internet, my name is Quinn and this is Blondihacks. I want to talk to you today about efficiency. Now we like to think that in a hobby like this, efficiency shouldn't matter, we're just here to have fun, there's no time pressure, we're not doing production, time's not money, yada yada. But the truth is, hobby machining is very, very time consuming, and if you want to ever actually finish anything, you do have to think about efficiency. That's especially perhaps true for beginners coming in who may not realize how important efficiency is in something like machining because it's inherently very, very time consuming. This is very different than woodworking or welding fabrication or crafting or other hobbies where you can pretty rapidly see progress when you're working on something. You can get a lot done in a day and really feel like you got something accomplished. And you can finish a whole project in a week, that type of thing. Machining is not like that. You will spend a lot of hours watching cutters traverse slowly over work. You'll spend a lot of time cleaning chips out of the vise between every cut to maintain your precision of your setups. You'll spend a lot of time changing tools. You'll spend a lot of time watching the head on your mill go up and down so that you can change tools. All of those things add up. Those are all things that you don't see in machining YouTube channels, so you might get a misleading idea of how long things take to make in a machine shop if you've learned it from watching YouTube. So we're going to talk about all of that right now. Let's start here on the milling machine because I think the milling machine is where you really feel efficiency improvements the most. Compared to the lathe, I think the mill is an inherently less efficient machine. Tool changes take longer, setups take longer, changing setups take longer, you change tools more frequently than on the lathe, so in general it's a more time-consuming machine. I'll break down my efficiency suggestions into categories. The first category we're going to talk about is tool changes, because this is something that you spend a lot of time doing on the milling machine, compared to the lathe where you might be doing lots and lots of cuts with a single tool, or you might have one or two or maybe three tools that you're doing for a particular operation. On the milling machine, pretty much every single thing you do involves multiple tools. Just to drill a simple hole, for example, is going to involve probably at least a center drill, a pilot drill, a main drill, then maybe a reamer, then probably a chamfering tool. A lot of tool changes for a single feature. So focusing on tool changes, how do we make those more efficient? Well, the thing that really kills you time-wise on tool changing on the mill is the variation in tool length. On the lathe, the tools are all pretty much the same length, but on the mill, they vary a lot. You've got little tiny center drills and gigantic reamers that all have to fit in this same space. And that means for every single tool change, you're talking about moving the head up and down or moving the knee up and down to make space for that tool. The first tip is easy then. Make all your tools the same length. Here we have a standard length drill bit. This is what's called a jobber length drill. And this is a stubby drill, or perhaps more technically a screw machine length drill. So called because in the olden days there used to be these things called screw machines. I suppose they still exist, but there were these things called screw machines that required a very specific length of drill. And that's these guys right here. Now the genius of screw machine length drills is, as you can see, they're all very short. And more than that, all the different sizes of a screw machine length drill are very close in size. Here I have a 1/8 and a 1/2 inch drill in jobber length and the same two drills in screw machine length. You can see that both drills are shorter than their respective counterparts, but more importantly, the difference between the drill length is much smaller on the screw machine length than on the jobber length. On the jobber length, the 1/2 inch drill is more than 2 times the length of the 1/8 inch, whereas here the difference is only 30–40%. And this difference gets smaller and smaller the closer in diameter the drills are. This makes a big difference in milling machine setups because you're generally working your way up in drill sizes, so from drill to drill, usually you can use the same head position for 2 adjacent drills, or at most you might have to move the head a little bit. But generally I can get all of my drills in a single head setup just using the distance of travel that I have on the quill when I use the screw machine drills. With jobber drills, that never happens. On a hobby milling machine, you've typically only got maybe 3 inches of quill travel, so there's no head position where you can get both this drill and this drill in range of the quill to get the travel that you need to drill your hole. This is definitely one of those things I wish I'd known sooner when I got into hobby machining. If I had, I probably would have gone straight to the screw machine drills and not bothered with the jobber drills until later. Now granted, occasionally you do need this length if you're drilling a very deep hole or a hole at the bottom of a deep feature, but it's incredibly rare. 99.9% of the time you're drilling holes in shallow material, and the short drills are just fine. The advantages go even deeper though, because not only are these drills close to each other in size, they're close to your other tools in size. So when you're starting with a center drill, you can see that if I'm drilling a pilot drill, my center drill and this 1/8 inch drill are the same length, and both are close in length to the very large drill. So already I've saved a bunch more head moving. Then when you get to your final operations, such as your chamfering tool, once again, we're all in the same size range of tool. So a single position on the head puts me within quill travel distance of all 4 of these tools. That is a massive time saving. Of course, the elephant in the room here is the reamer. If your hole is going to be reamed, then you are going to have to move the head for this because these things are very, very long. Now, stubby reamers do exist, but they're hard to find and they don't do as nice a job because reamers are this long for a reason. You want them to have some flexibility in the shaft because they need to be able to self-center very effectively on the hole in order to make the hole nice and round and accurately dimensioned. But even with the reamer in the loop here, we've saved 1, 2, 3 head movements just by using this set of tools. So making all your tools the same length saves you tool changing time. Making all your tools the same diameter also saves tool changing time. Something you do a lot on the mill is edge finding, of course. Generally, every single setup that you do requires another edge finding operation. So I have 2 edge finders. Why? One is 3/8 and one is 1/2 inch, because 90% of my milling cutters are 3/8 or 1/2 inch. So most of the time when I'm doing a series of operations, I've got one of these 2 collets already in the spindle. So when it comes time to edge find, I can grab whichever edge finder matches the collet that's already in the machine, saving me collet changes. Again, that may not sound like much, but changing a collet also often means moving the head up and down. And then you got to dig the other collet out of the drawer. And then you got to do it all again in reverse when you go to put the cutter back in. So the simple act of owning 2 different sizes of edge finder has saved me a lot of time over the years. Of course, as the software engineers out there know, the best way to optimize something is to not do it at all. So the less edge finding we can do, the better. And there's a whole bunch of ways that we can reduce the number of edge finds that we need to do through a series of operations. One of the best is an end stop. What an end stop does is it gives you repeatability on your vise in the x-axis. You've always already got repeatability on the y-axis because of the fixed jaw, so make sure you're leveraging that. The fixed jaw is always your reference on the y-axis, and that doesn't change when you go from part to part. You may find yourself doing a lot more edge finding on the y-axis than you actually need to if you remember that fact. But on the x-axis, we have no such advantage. The end stop is what gives us that. These come in a lot of different forms. I've made this one here. I have a video on making this that clamps to my vice jaw. People will often make one that screws into the end of the vice jaw as well that flips down. You will also often see me using a magnetic indicator stand sitting over here on the table as an end stop. Those work great. This simple tool, though, is an incredible efficiency gain because what it means is every time I put this part in here, all I got to do is slide it up against that end stop, and this thing is in exactly the same X position as the previous part was, or when this part was when I took it out to change my setup, and so on. This generally saves you 1 or sometimes even 2 edge finds if your reference is the center of the part. Sometimes you can't avoid doing the edge find. However, you don't always have to do it with an edge finder. Think about what an edge finder is actually doing. It's telling you where on the milling machine the surface of a part is. However, there are other ways to do that. For example, you can edge find with the cutter that you're about to cut with. If I start up this cutter and move in very, very slowly with the table until I just see the tiniest little wisps of shavings coming off of that surface, then I know that this cutter is on or ever so slightly below, maybe a couple of tenths below that surface. Then I can zero my DRO there and program in the radius of this end mill. Presto, you've done an edge find and you're already set up to do your cut. The accuracy of this method depends mostly on how slowly you're willing to feed the table. The slower you go, the more accurate it will be. Obviously, a traditional mechanical edge finder is non-destructive and more accurate. However, that doesn't always matter. For a lot of cuts, just doing a simple touch-off with the end mill is accurate enough and will save you a lot of time. A lot of efficiency gains in the machine shop come from knowing when ultimate accuracy and precision matter and when they don't. Precision costs time, and incidentally, that's also why precision is expensive. So by calibrating the precision of your work to where you need it and where you don't, you will save yourself a lot of time. I think that last lesson is a tough one for beginners because many of us get into this hobby because we're excited about the prospect of making things as perfect as possible, and you really want to do everything flawlessly and you want every single cube to be micron perfect. Well, pretty soon you're going to find out that A, that's a lot harder than you thought it was to actually do in the real world, but B, that takes a lot longer than you thought it was going to. The novelty of that micron perfect cube wears off pretty quickly when you realize that a 1/10 of a millimeter accurate cube is good enough in 99.9% of cubes and takes about 1/10 of the time to make. There's one other way that you can use an end mill as an edge finder, and that's if you're machining both sides of the same part. If this stock is over length and I'm going to be side milling this side here to square it up, and I'm also going to be doing that on this side, then simply do them in one setup. Mill this side, then move the cutter over the dimension of your required part plus the diameter of the cutter, make your cut over here, and you've saved yourself multiple edge finds and your part will be extremely accurate in dimension. How extremely accurate depends largely on how much you paid for your end mill. The dimensional accuracy of end mills does vary considerably by manufacturing quality. Generally, if they're poorly made, they tend to be on the small side, so you may find yourself a little bit oversized. Luckily, that's a forgiving error. You can just make another cut on this side. Of course, cutter wear can contribute to that. And then the biggest contributor to error in this method is cutter and quill deflection. If one of those two cuts is a heavy one, then the end mill and or the quill are both going to deflect slightly, and you're going to end up with a side that's not as square as it could be and is also probably over dimension. But again, accuracy where it matters, most of the time that's going to be accurate enough. The next category of efficiency gains comes from order of operations. Now this varies a lot by part and by project, so I can't necessarily give you specific advice, but I can give you a really good example. So something you might commonly be doing is drilling and tapping a whole bunch of holes on a part, or drilling and tapping the same hole on a bunch of different parts. So here is all of the tools that I might be using for this operation. I'm going to be center drilling, pilot drilling, tap drilling, and then tapping with my spring-loaded tap follower. And every single one of these is a tool change. Even though I've, again, optimized everything for tool length so I don't have to move the head a lot, I'm still doing a lot of tool changing. So if I'm going to be doing 10 or 15 of these holes, that's really going to add up. So in this case, it's going to be more efficient to do my center drill on all of the holes, then my pilot drill on all of the holes. Now on a single part, that's easy because you've got one setup, you're just moving from hole to hole. The DRO really helps there. If you're having to manage backlash, then that's going to be much more of a hassle. But with the DRO, you don't have to worry about that. So you can jump from position to position easily with no precision loss. So it's much more efficient to do the same operation on every hole, then change tools once, do that operation on all the holes, and so on. There's always going to be a sweet spot there where if you're only doing a couple of holes, then it might be more work to move back and forth. Or if you're doing multiple parts but you can't or don't have an end stop set up for whatever reason, so changing parts would cost you your positions on the DRO. If the part is very large, it might take more time to be moving back and forth across the whole part, even with the power feed, than it is to just change the drills. So it depends a little bit. There are occasions when it's more efficient to do all of the operations on a single hole and then move on, but in general, it's going to be more efficient to reduce tool changing. One more way to save time on edge finding is right here on the DRO. Every DRO has at least 2 coordinate spaces. You've got your absolute and your incremental scale. Now there are many different ways to use these 2 scales, but at its most basic, it's 2 independent coordinate spaces. That can save you a lot of time because, for example, it allows you to do multiple part setups in the vise, where you do a bunch of edge finding on both parts in the same setup using the absolute scale for one part, then edge finding on the other part with the incremental scale, and that saves you tool changing for those 2 parts. You still have to do 2 edge finds, but you don't have to change the tooling in and out for the edge finds between parts. That can be a big time saver. In fact, a lot of DROs have a lot more than just those 2 coordinate spaces. They usually have some sort of datum feature in them that allows you to store hundreds of different coordinate spaces, but that can get pretty complicated. Just using absolute and incremental as 2 different origins in itself is a big time saver. Let's try and save some time over here on the lathe next. Now, tool changes are generally less of an issue on the lathe because, of course, we have things like quick change tool posts. The whole point of a system like this is that all of the dovetail surfaces and other references on a tool holding system like the Aloris is that everything goes back exactly where it was and different tools will all repeat in the same positions on the same tool post. However, the gotcha on the lathe is tool post angle. If I'm going to use a standard left-hand turning tool like this, regardless of whether it's carbide or high-speed steel, yes, I can turn with this tool, but if I want to also do a facing operation, I might need to either change tools, or more traditionally, you would use a tool like this with the tool post at an angle so that you can feed the tool across the face like so. And the reason you want to do this is because you want this cutting edge to be square to the surface that you're cutting so that the tool geometry is correct for a nice cut. But that requires rotating the tool post between cuts. And that's a bit of a killer time-wise on the lathe because every time you change your tool post angle, you need to square it up again when you go back to normal turning. Now, I've talked a lot in previous tips videos about how to square up the tool post. Generally, it involves running it up against something else that's square on the lathe. It can be the surface of a chuck, it can be the surface of the work if it's been faced, it can be the surface of the tailstock quill, it can be a 1, 2, 3 block up against a reference like the mounting plate here for the chuck. Lots of ways to square up the tool post, but they all cost you a little bit of time, and that can add up. So on the lathe, for efficiency reasons, I focus on ways that can reduce any amount of tool post angle changing. One really good way to do that is to choose tool geometry that can face and turn with the same tool post angle. One such example is the tangential tool. I get asked about this tool every single time I use it. It's called a tangential or diamond tool holder. This is a very old school tool holder. They used to use this style at the turn of the 19th century. They were pretty popular because of the simplicity of the grinding of the tool bit. But they also have the secret advantage that they do a really nice job of facing and turning with a single tool post angle. There are, of course, modern ways to do this. It's pretty common to see dogleg insert tool holders that give you a reasonable tool angle for good cutting geometry on both facing and turning. This one happens to be angle adjustable, but most of them you'll see are just a fixed dogleg that hold the insert at an angle similar to what the tangential is doing. And this again allows you to get reasonable cutting geometry for facing and also turning. So this is a big time saver. Another way to achieve this time saving is to have both right hand and left hand turning tools of the same type in your arsenal and keep them both mounted up on tool holders. This way, I can drop that one in for turning and drop that one in for facing. A left-hand tool on the back of a squared up tool post has the ideal geometry for facing cuts. And in fact, the geometry of this setup is actually better than most of the other things that I've showed you. Typically, any kind of cutter that's at a bit of an angle and being used for facing cutting is always going to be a compromise. It's going to work okay, but ideally, the ideal tool geometry is always to have the cutter squared up to the surface so that the geometry on the top of the tool has the correct lead angle that it was designed to cut with. If you're doing light facing cuts, which is the norm, then it usually doesn't matter very much, but if you're doing heavy cuts, if you've got a lot of material to face down, then you want to use the correct tool geometry for best results, and that's where the left-hand tool really comes in handy. Back in the day, they used to have dedicated facing tools which looked very much like a grooving tool that were designed to do heavy cuts that pushed straight in, and they'd be mounted here. And those were used in the days of lantern tool posts and things like that, where you didn't have multiple tool post mounting options, so a dedicated facing tool that had the correct geometry for pushing straight into the work could save you a lot of time. The final category I want to talk about are more general shop quality of life kinds of efficiency improvements. Here's a very simple one. I have a magnetic spring clip on the backsplash on my lathe. That allows me to put my drawings right here in my sight line while I'm working on the machine. This is a big time saver and actually an error reducer as well, because I've always got this to glance at in an instant before every single cut. I can always just be constantly monitoring myself, making sure I'm doing the right things in the right order. If this drawing is sitting over on your bench somewhere, You're wasting more time than you think you are walking back and forth and checking the numbers on that drawing. Furthermore, during all of that walking back and forth, you're holding a bunch of numbers in your head. You're more likely to jumble them or forget one of them and mix them up and blow a dimension. Being magnetic, this clip also makes an excellent chuck key storage area, and this keeps the chuck key right next to my tailstock where you need it all the time, which again saves a little bit of muscle motion for something that you do hundreds of times a day. This kind of stuff really adds up. You know, back in the days when manual machine shops were doing production work, they used to do these things called time and motion studies in factories. Maybe they still do. Yeah, they probably still do. And honestly, they were pretty cruel to the workers. It's one of the reasons we have unions today, where you'd get a suit who'd come in and watch you at your machine and decide where you were moving your arms too often and where things could be improved to save the boss's money. It was a pretty terrible thing back in the day. But nowadays, ironically, doing it to yourself for fun is kind of a great idea. Carrying on with that lifestyle theme then, there's a lot of efficiency gains to be had simply by how you lay out your shop. I've talked about general shop layout and tool organization and so on in other videos, but in particular I want to focus on this area here. This is what, to quote Adam Savage, is my first order of retrieval area. These are all the tools that I use not only every single time I set foot in the shop, but hundreds of times a day. So any small efficiency improvement in access to these tools is going to save me several minutes a day and hours over the course of a week. Obviously you can see what I've got here. I've got my smallest micrometer, my pencil, my scriber, my scale, my calipers, and well, the height gauge lives here just because it's tall and I don't like to put it sideways in the drawer where it's going to get bent and so on. But the point is that the frequency of use of these tools is so high that it's not worth putting them away. They literally live on the workbench because putting them away at the end of the day, or God forbid, putting them away between every use, is a total waste of time. So they live here and they don't even get dusty because I use them so often. The other win here is that this little area is centrally located in my shop. You can't see it, but my lathe is right there, my mill is right there, and my other workbench is right there. And then of course you can see this workbench here. So this little area here is chosen because it's literally within arm's reach of every single work area in my shop. Not counting the grinders and stuff, which are way down there, but they don't need to be used with these tools. The other reason this little area worked for me was because it's on top of the surface plate cover, so it's kind of otherwise wasted space. I don't want stuff to pile up on here because otherwise I can't access the surface plate. I don't want to bury my surface plate in books and other debris that tends to accumulate on horizontal surfaces. However, just having this small collection of lightweight tools on here means I still have instant access to my surface plate. This particular setup works for me. I'm not saying it's going to work for you, but the general idea, I think, of this first order retrievability of your most crucial tools is a big win. Now, I would not go too far with this personally. You'll see a lot of folks that have every single tool hanging on the wall or sitting open on rolling carts and things. If that works for you, great. Personally, I'm not a fan of the hang everything on walls and keep it all out in the open approach, because then everything gets dirty and it creates clutter and there's negative externalities both physically and mentally with having all of your tools out like that all the time. Again, my personal preference, you do what works for you, but for this little collection of tools, first order retrievability, a big win. Incidentally, I didn't sit down one day and decide these were the tools that needed to have that special significance. This just developed organically. As I've spent more and more hours in my shop, now I spend most of all day every day out here. These were just the tools that I found myself leaving out at the end of the day and needing the first moment I came in the next day. So it just kind of organically developed that, okay, these are the tools that I shouldn't bother putting away. Well, that's my little speech on hobby machine shop efficiency. I hope there was something in here that was useful for you. If you've got efficiency tips that you want to share, put them down in the doobly-doo. I'm sure that you've got good ideas that I've never thought of, and other people will too, so let's all help each other out a little bit. Thank you very much for watching. Thanks especially to my patrons for making all of this content possible, and I will see you next week.